All right, let's look at this example for differential equations. First order linear, we have an existence and uniqueness theorem. So right here I have a first order linear differential equation with an initial condition. Let's find the largest interval where we are guaranteed a solution, a unique solution. So first, we need it in the standard form. And by that, just mean we need a 1 as a coefficient in front of our largest derivative. So if I divide through by t, what do we have? We have y prime plus 3 over t y equals 1 over t to the fourth minus 81. The initial condition is still y of 1 equals 3. We call this p of t, call this g of t, and we need intervals where both are continuous. So if I look at p of t first, 3 over t, this is continuous on everywhere but, well, 0 is a trouble point. So negative infinity to 0, union 0 to infinity. Say it's continuous on each of those two intervals. G of t, 1 over t to the fourth minus 81, is continuous everywhere except at plus or minus 3. So negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. So I now need intervals where both functions are continuous, so essentially take the intersection there. So both p and g are continuous on I'm going to fit it here. Negative infinity to negative 3, negative 3 to 0, 0 to 3. It won't fit. Oh yeah, well, union 3 to infinity. Squeeze it in there. So what do we got? 4 intervals. So on any of these 4 intervals, both functions are continuous. If I made any interval larger, then one of the two would not be continuous. So these are the largest intervals where both functions are continuous. So for our initial condition, y of 1 equals 3. That's our t naught, initial condition. Which interval contains that? And that would be this interval. Yeah, put it this way, t naught equals 1's inside that interval. So 0 less than t less than 3, or in interval notation, 0 to 3 is the largest interval. Guaranteed by the theorem. So we're guaranteed a solution to, if I put it in standard form, so there we go. So 0 to 3, that's the largest interval. It's possible that we can be more than the largest interval guaranteed, but we're guaranteed at least that interval. And usually that's all you get. And as we'll see when we actually find the solution, that will be all we get. Before we do that, if we look at B, so same differential equation, but now y of 4 equals 2. Well, all we have to do is look at what's the t value for which interval, which of those 4 intervals does that belong to? 3 to infinity. So so there's a curve that'll go through this point, and it'll keep going to infinity, and it's good till at least 3. The open interval, 3 to infinity. Just put it like that. So generally, that's all we need to do when we're just asked to find the interval. Use the theorem, just find the largest interval where we're guaranteed a solution. But this one was made so we can actually find the solution. So let's go a little above and beyond and do that. So back to part A, and I know I didn't label it part A, but I'm treating it as part A. Y prime plus 3 over t y equals 1 over t to the 4th minus 81. So we have our p of t. We'll do our integrating factor. I'll call it mu of t. So that will be the integral 3 over t dt. So e to the 3 log t log of t cubed, which simplifies nicely to t cubed. So there's our integrating factor. So let's see how we solve it then with that. Keep going here. So if we multiply the standard form by our integrating factor, and we can sometimes skip some of these steps, but I'll show them. Just in case we're rusty on any of this stuff. Alright, so there's the original differential equation multiplied through by both sides by the integrating factor. So the left-hand side should become the derivative of your integrating factor times y. And the right-hand side, if I just do this, and then you can double check to find if we were to use the product rule, say the first derivative of the second, that would be distributing here. The derivative of the first, 3t squared, that's what happens if I distribute there. You end up with 3t squared y. So derivative of the first times the second. Alright, so the derivative of this is that, so this is the antiderivative of that. And maybe a little bit of sketch of what we would do. Substitution, say if we let u equal the denominator, then du would be 4t cubed dt, or 1/4 du would be t cubed dt. Kind of have a t cubed dt there, so this would be a 1/4 log u. So t cubed y maybe I'll put it, kind of mix them up a little bit here. So we'd have a 1/4 log u plus c. And maybe we should put absolute values there, but I can get away without doing that. We'll see why in a bit. So I won't put the absolute values. T cubed y, 1/4 log, back substitute here, t to the 4th minus 81. The way I'll get around not having the absolute values, I'm going to absorb this constant into the logarithm. So t cubed y is 1/4 log of k times t to the 4th minus 81. So look at it this way. I'll expand as well. So we actually will kind of look at it with an absolute values, but just from known properties of logarithm, log of AB, log A plus log B. So if I have this times that, if I were to expand, essentially C is like my 1/4 log K. This doesn't need to be written, but or my K would be e to the 4C. But anyway. So if we put in our initial condition here, y1 equals 3, then we've got 1 cubed times 3 is 1/4 natural log, so 1/4 log of k times 1 minus 81. So it seems like we need the absolute value there, right? We're going to have a negative. We all know we can't take the log of a negative. But let's continue anyway. 3 times 4 is the log of negative 80k. Exponentiate. Divide, and we have our k. So put the negative like that. So if I substitute this in, solve for y, we have y equals 1 over t cubed, 4t cubed, there it is, natural log of this expression, or this constant, I should say, times t to the 4th minus 81. And in a way, if I were to distribute this negative, it was as if I did the absolute value. But it might look nicer to actually do that, but I'll leave it like this. So there's the answer. And now we can see there's trouble at t equals 0 and at t equals 3. All right, so we're going to run into the natural log of 0 at t equals 3. So we'll run into trouble there, and of course we divide by 0. So that's why there's trouble for this thing. You can actually put 0 on the inside of the log here. You'd have negative 81, but then times that negative, it's positive, and you can see what we get. In fact, we can even check our initial condition at least. So y at 1 is 1 over 4, 1 cubed, natural log of negative e to the 12 over 80 times negative 80. Simplify that. So that cancels in the negative as well. So we have log of e to the 12, which will just be 12, 3. Perfect. a little quicker here, we'll look at part B, but we can just work right here when I put in the initial condition. Everything else would be identical. So no sense redoing that. So all I have to do is put in a different initial condition. B. So y of 4 equals 2. So I can't quite see it. It's right about there. So we would have 4 cubed times y, 2, equals 1/4 natural log of k times 4 to the 4th minus 81. And that's going to be negative 175. This will be 512. I multiply that by the 4. It's natural log k times negative 175. So if we exponentiate e to the 512 divided by negative 175. And I'll write our solution. Y of t, I'll put in the t notation this time. 1 over 4t cubed natural log negative e to the 512. Might put this in another format as well. Oops. 175. My eyes are all over the place. So there's the k, the e, negative e to the 512 over 175. Yeah, I'll just rewrite it. Next page. Times t to the 4th minus 81. Look at it. Checks out. I won't put it on paper, but if you plug in 4, you get 256 minus 81 is 175. 175 cancels, and that leaves me with, pretend this negative's not there because it shouldn't have been there. This was positive 175. So correct all this in post. There we go. So good thing I checked. So now plug in 4, 256, 175 cancels. Log of e to the 512 be 512 divided by, if you plug a 4 in there, you get 256. 512 divided by 256 is 2. All right, so let's recap then. The differential equation, y prime plus 3 over ty equals 1 over t to the 4th minus 81. And the initial conditions where y of 1 equals 3 and y of 4 equals 2. So solution was y of t equals 1 over 4t cubed natural log. Then I had negative e to the 12 over 80 times t to the 4th minus 81. But this can be written as, put the 4t cubed down here. If we take the log, I'm going to put that minus inside, so I have log of e to the 12 will just be 12. And then we'll have plus natural log of 81 minus t to the 4th. All right, so that minus went into here, made it 81 minus t to the fourth, took that log, and then minus log of 80. And we can use this to analyze the curve, what's going to happen. I mean, you kind of see from 0 to 3 is our domain here, at least if we're going to go through 1. It actually also works from negative 3 to 0, but we've crossed 0, stops it. So 0 to 3 for that initial condition. For part B, y of t, very similar. Natural log, so here was e to the 512 over 175 times t to the fourth minus 81. So that equals 512 plus log of t to the fourth minus 81 and minus log of 175 all over 4t cubed. Alright, so that recaps our answers. Again, it's going further than generally go in these type of questions. Usually it's just to find the interval. You don't have to solve. Here I did solve. It's a little harder than usual maybe to find the solution. Put it in a couple forms because I want to look at, eventually I started graphing the solution, right? So I first modified. I think I came across a similar problem, but it was like a t squared. Maybe I just needed a t up here, I don't remember. But just to make it a little more interesting, I made it like this. But let's see. So if I look at our graphs, let's see here. I want to go to this one. There's our differential equation. Here's my direction field. Notice I don't see any problem points, and I didn't think anything of it for a few years. Here's my constant to make my function. So there it is. Let's put this up a little. So there's the graph of the function that goes through 1, 3. Again, it goes to 3 and kind of stops. Goes up here. It does go to plus infinity. So again, there's the graph. And it's kind of hard to see why it stops looking at this direction field. I mean, the direction field looks pretty nice. Doesn't seem any reason for it to stop as far as I can see looking at this. If we look at our other solution, goes through 4, 2. There it is, goes through 4, 2. And again, it's going up to 3, and then it kind of stops. Kind of wonder if it went to plus infinity, but no matter how high I graphed, it didn't go up. So it looked like it just stopped, as far as I could tell just from graphing. If I look a little more, well, eventually I stumbled upon a luckier pick of the number of arrows or whatever you want to call these to plot, and I kind of saw the wall at least at 3 and negative 3, and you can also see one kind of on the x-axis. If I change this axis here, right, so in the x-axis there looks like there's a wall, and there kind of is, like eventually if we have a solution here, we won't be able to cross. We'll come back down. Put the axis back to normal though. So if we look at our plot, well, I can now see it go through 1, 3, then looks like it runs into a wall. And does it just stop? Similarly, coming the other way. Runs and just hits there, and does it just stop? So, eventually, I got curious. Took a while, but eventually I did. And it wasn't too hard to see. Whoops. There's a lot more to this than meets the eye here. So let's look. We can actually analyze this particular answer and see what's going to happen. But let's analyze the direction field. Or the derivative. Alright, so if I solve for y prime, what do I get? I get negative 3 over t y plus 1 over t to the fourth minus 81. And if I want to look at, say, what happens, limit as t goes to 3 from the left of y prime. That's going to be roughly, well, this will just be roughly y, and that's going to be some finite value. And this is where it's blowing up as you go to 3. And if we're going to 3 from the left, we're not yet 81, so this will be a negative. We're headed towards 0, but on the negative side, I kind of put a plus 1 over 0, but on the negative side, that's going to go to negative infinity. So if I look at the, oops, that was supposed to be at 3. See, there's the x-axis. So if this is at x equals 3, we should have a negative slopes. We don't see them, but we will. If we go to 3 from the right, again, this will be roughly, I mean, that'll just be, what did I call this? It should actually have been negative y, but it won't affect anything. Negative y. And now this will be plus, now it's, again, it's going to 0, but from above 81, so it'll go to plus infinity. So on the right hand side, which means the curve should be going to negative infinity. That. And if you look at the limits, they do, I mean, either way you look at it, a little bit easier this way. But as you go to 3, again, that's just going to be like a fix. So this is almost like 108 in the denominator. You got these constants, which don't affect much. But then over here, you're going to log of 0. Right? If you're less than 3, this is always positive, but headed towards 0. So this is going to go to negative infinity. And similarly, here, if you're bigger than 3, this will go to negative infinity. So both curves go to negative infinity. This one goes to negative infinity, this one goes to negative infinity. As expected. And then it's not too hard to see. And then it's not too hard to see as you go to infinity. I mean, this curve will just go to 0, right? This goes to infinity, but much slower than the denominator does. And if we were to look at the slopes, they're going to go to 0. So as you go to infinity, it's going to level. So if we go back and look at some plots here. So here we are, again running into the wall, but now I'm going to zoom in. So I haven't zoomed in too much yet, but again, this is negative 5 to 5, and I'm going 2.5, 2.5. Let me zoom in the y's first. I'll zoom in near the origin. So let's see. let's go from negative 0.1 to 1.1, or no, 0.1. And I don't know if I need to fix the x's yet, but let's wait. So there you can actually see it. So you can actually see the direction fields are all negative, and we're going to go down. Although here they're kind of zeros. This 0 is going to travel to the right gradually, but again, it essentially is like what I said it should be. If I make this smaller, so this is the x. So go in 3, I went plus or minus 5, and that'll be plus or minus 1. So 2.9 to 3.1. So again, and if I change the y's, it won't matter. So if I go from, say, negative 4.1 to 3.9. So negative 3.9. Well, we kind of lost it, so which is good. So it doesn't look like, at least on the left of 3, like we're going down. But again, if you zoom in closer, so let's go make h equal 0.01, and there it appears, and you go down. So if you just zoom in enough, it'll go from the increasing to the decreasing, but it does so in really close to the 3. So for some more analysis, let me first go to the paper. Just to ballpark it. So again, if I look at this, 81 minus t to the 4th, so t is going to 3 from the left. So let's just say t equals 3 minus 1 over n, and then n will go to infinity. Then what I have for the y of t, I have 12 plus natural log of 81 minus t to the 4th. That'll be 3 minus 1 over n to the 4th. Then minus log of 80 all over 4t cubed. Alright, so just, oops, not that one, this one. Change that t to a 3 minus 1 over n. And we're going to let n kind of go to infinity, so we'll get closer to 3. So then this will be put this first. So log of 81 minus, well, if you know your Pascal's triangle, you get 3 to the 4th plus 3 cubed times negative 1 over n, and I forgot the times 4. That almost looks like a 4. Not quite, but yeah. As long as you heard me say it out loud. 4 times this, because I need parentheses. And then plus 6 times 3 squared. All these terms get dropped anyway. Times negative 1 over n squared. And plus 4 times 3 times negative 1 over n cubed. And plus negative 1 over n to the 4th. So I ran out of space. So that was just this part. And then I got to add those two things. I guess I'll put it here then after all. So 12 plus that, and I also need the minus log of 80. Just write it right here. Minus log of 80 goes after. So let's see what I have. So this will be 81. They're going to cancel. So I guess I'll keep this first then. 12 plus log. Then if I distribute, that's 27 times 4. That'll be 108 minus a minus, so 108 over n. And I think I'll just drop the other terms at this point. So plus order of 1 over n squared. And you have minus log of 80. And then this 4t cubed. So if I'm almost 3, I might as well just call that a 3 down here. So we'll just call this 108. Coincidence, these are both 108. So take a look at what we have then. So y of t is going to be, I mean, this is, at this point, I've ballparked it at this point because I dropped some terms. But these go to 0 so much faster, right? So just for example, if we were to take log of 0.0001, 0001, 0001, whatever, I mean, that would be roughly log of 0.0001. Right. If you drop these terms are much closer to 0. If you do this on the calculator, they're going to match. So essentially, that's what I've dropped. Right. So once n is like 100 squared, puts it out like that, or 1,000. I guess this is almost like 10, 100,000, 10,000. N's around 10,000 right here. Anyway, but these terms can be dropped. So we've got 12 plus log of 108 minus log of 80, and then minus log of n all over 108. So that's roughly a negative log of n all over 108 plus a constant, which I called a. A is around, these two are almost cancel perfect. You almost have 12 over 108, which is 1/9, so a is around 0.11. So this kind of ballparks the function when we're really close to 3, right? So if t equals 3 minus 1 over n, n large, y is going to be roughly the negative log of n over 108 plus a tiny constant, 0.11. And I can actually use that, like what if I want y to equal -2, then you should have -2 equal negative log n over 108 plus a. You do some math. You'd subtract, so -2 minus a times -108, and that would be log n. So n is e to this. And in general, what if I want y to equal, I'll just call it m. Then n is going to have to be e to the negative 108 times m minus a. Let's make sure that's the way I have it here. Yeah, well, I just have it as e to the 108 times negative m plus a, same thing. So that's how big n has to be if you want to reach that. Oops, we weren't looking. So let's look at what I just had on paper there. So there's my function, the original, and here's the plot. There it goes. Yeah, that's what we saw before. Look, I kind of you can see it dip down a little. Now, if I zoom in, it looks a little flat and then goes down. Where am I at? So I'm around like at 0.05. It looks like it's going down. But now if I zoom in, that was the Y value. Again, here I am at 0.05. Now it's flat again, then goes down. And it's always going to be like that as I keep zooming in. I always keep 3 on the right, but keep zooming in on the left here. All right, so if I'm 2.9, so this is at 2.9, 2.92, etc. This is at 2.999. And if I zoom in more, gradually cross the x-axis. When I zoom in, it always looks flat until right at the end. Again, so at 2.9, I was about at 0.1. At 2.99, I'm at 0.07. Here's the value to reach about -2. G of 2.9999. And I find that by doing the work I mentioned before. Right, so there's G of, if T is 3 minus 1 over n, that's the 1/4 and so forth. But putting in the 3 minus 1 over n for the T and expanding, and then dropping the 1 over n squared, 1 over n cubed, and 1 over n to the 4th terms, they go to 0 much faster. So if you're going to keep these first two, then of course 81 minus this gives me just this, positive, right? So at 81 right here, 81 minus this. So now it's, now I have that. And then if I made the denominator, I mean it's roughly 4t cubed will be 108, and those other terms. So there's the A I mentioned before, which is roughly 1/9, but a little bit off. H is going to be that. And then you can compare my approximation to the exact G. It's not too bad, but here n was 100. Now here's n square that 10,000. They match a little better. Now, what am I at to? Looks like, is that 1 million or 10 million, I think. Can't tell. So 10 million, and then this matches. So 3 minus 1 over 10 million would be this value. And then, as I did before. So what value? If I want the function to reach -2, this is what n has to be. Almost 10 to the 100. And then 3 minus 1 over that. So that's how close to 3 we have to be. Again, this is like 1,200 digits right there. But 2.999 for a while. And if I do G of that value, I'm at about -2. But I want to reach some other values. Like, what if I want to reach -10? We will. That's about 2.4 times 10 to the 474. Huge number. 10 to the 474. 1 over it is so tiny. And 3 minus, you're pretty much at 3, but not quite. So, not quite at 3. And G at that value is about -10. If you want to reach -20, I think we get the idea, but enjoy it anyway. 2.6 times 10 to the 943. So, I mean, such a huge number. 1 over it is so tiny. 3 minus, you're right, I'm pretty much at 3. And g at that value, you're at negative 20. About the last one I can do with my 1200 digits that I saved. If I go to the top. So I told Maple, let's work with digits 1200. And go up to 25. Right, so I'm just about at 10 to the 1200. So 8.6 times 10 to the 1177. 3 minus, so out of the 1200 digits, they're almost all 9s now. So we're almost at 3, but not quite. And see, so g would be at negative 25. And again, in theory, we can plug in anything here. I can go to 100. So we go to negative infinity. Plug in any negative number and we'll reach it. If I want to reach negative 100, it has to be at 10 to the 4,695. This won't work now. This will say 3. Yeah, and I went to negative infinity. So, but it's really 3 minus 1 over that number. And I didn't put in enough digits for that. But I can actually still do this. 3, if I want to reach negative 1,000, so there's the number. It's really from here. And so 1 over that number, so close to 0. 3 minus 1, that, very close to 3. So I think we get the idea. If I look at my plots again, so here we are with a kind of a nice direction field. We just kind of see that vertical there. Solution, etc. I didn't want to see that, but I mean, here's points in kind of 8 different regions. Positive y, negative y, and in those 4 intervals. And if I look at the solutions, oops, it takes a little while. But there we go. It's not trivial to know what's that behavior. But I did it before, and let me pull it up then. Oops. There it is. So it's already been drawn on, but we'll take a look. So from this differential equation, so what's going to happen? You're going to go to negative infinity, negative infinity, negative infinity, negative infinity. So we kind of analyze that. Maybe I'll look at this side again. Look at, there's a little maximum there. But here you'll never be able to cross the x-axis. You'll hit that boundary and not be able to cross. But here you do bypassing, cross and go to negative infinity. But I can use that approximation to solve for where the max would roughly be, where the horizontal tangent would be. You can use the approximation here to kind of find, well, in this differential equation, kind of solve for where it's 0 using that approximation. But anyway, and from there then you go down to negative infinity. So you won't cross the axis on this region. And it kind of turns out the graph, if you spin it 180, you get sort of the other half. So these both go down, or these both go up to infinity. This goes as a min, then goes to infinity. These go to infinity. I didn't look at as you go to 0. I'll just do that right here, right? So if I look at the derivative, t goes to 0, say from the right of the differential equation. actually, well, I'll just put in what it equals here. It's going to be, oops, I want to look at it. So as you go to 0, this will go to negative 1 over 81, right? 1 over negative 81, whatever. And that'll just be fixed. But this has a y, so it'll go to, well, maybe I'll put it in that way. So negative 1 over 81 minus 3y over t. So this will go to, if y is positive, this will go to infinity, negative infinity. With the limit as t goes to 0 from the right of y prime, that will equal the limit as t goes to 0 from the right, negative 1. Well, I'm kind of repeating it, but 3y over t. This will go to plus infinity if y is positive, right? So now the y matters. So plus infinity. So these are always going to be like this. So you're going to go to negative infinity this way. I mean, the slope is increasing, which means you came kind of this way. And here the slope's negative, which means you come down that way. All right, so that's an over-analysis of the curve. Actually, let's look at the one here too. So this was the part B. So there's the G. So there's the curve. Looks like it just stops. I couldn't figure out why for a while. But if you zoom in, you see a little, it starts to go down. And zoom in more. Going down. It would be the same analysis, so I won't say too much about it, but did have Maple do the calculus and solve. So the derivative was 0 at roughly 3.002. And then the y value came out to be about 4.67, which is what you can actually see right here. So about 3.002, so almost right, exactly right there, was the max, and 4.67 for the y value. But the curve goes down to negative infinity. I mean, similar math. You can ballpark it and have it go as negative as you like. So what I have here going on. And that's all right. Skip all that, but it goes to negative infinity. All right. Over analysis over. I should also add that if we look at the early graphs, we can't always see like what was going on. Oops, not quite that early graph. Where's the early graph? Here we go. All right, so if we look at these curves here, you can see why the problem is. Technology doesn't exactly show it to us, so we have to have an understanding of what's going on. There's a tendency to totally rely on what technology is showing us, but if you don't have any understanding, sometimes it'll steer you wrong. And I don't know if we got steered wrong, but we weren't exactly shown what's really going on just from what we saw here. So we had to delve deeper and use some analytical techniques to figure out what's going on and see that we actually do go to negative infinity. It doesn't look like we would, but it does happen. So bravo for us.